Hello, Algebra 2 students. Today we're going to start talking about logarithms. Now, to kind of give you an idea of what are logarithms, what is the purpose of this thing that we are going to learn about, which is logarithms. Now, when we have equations like 2x is equal to 4, we see that 2 is being multiplied by x, or x is being multiplied by 2. So we want to use like an inverse operation to get x by itself. So we would like divide by 2 on both sides to get x is 2. Right? Or if we had something like x plus 1 is equal to 3, we see that 1 is being added to x, and to get x by itself, we want to use an inverse operation to addition, which would be subtraction, so you subtract 1 from both sides to get x equals 2. Or even if we have something like x squared is equal to 9, x is being squared, we want to use the inverse operation of squaring to get rid of the square, and to do that we square root, and we'll get x is equal to 3. So we use these inverse operations when we're solving for x in these equations. Now here's the catch. What if I had something like 2 to the x is equal to 4? Currently we don't have the tools to use the inverse operation of that exponentiation of x. But mathematicians have discovered logarithms many years ago, which is the inverse operation of exponentiation. It's a logarithm. So that's kind of why what we're going to learn is important. We are learning a new operation which undoes this exponentiation of x. So it will become very useful for many applications, including but not limited to solving problems where x is stuck into an exponent. Okay, so in my own words, how would I describe the logarithm of y with base b function? So if I have x equal to log b of y, then really how I would describe that is that's the, this is only true if and only if b to the x is equal to y. All right, so these two things right here and here, they give me the same exact information. And in fact, it's quite easy to rewrite one in terms of the other. And you'll see that fairly shortly here. But actually, let me show you just with the variables. So if I have log base b of y is equal to x, we could rewrite this starting at the base. Right, so we have a base of b, and then going to the other side of the equation, that's going to become the exponent, and then it's equal to the argument of the logarithm. Right, so that's how we can transfer from here to here. And you can transfer back just as easily. Right, so log base b, of y is equal to x. Right, many teachers you'll hear say something like, they'll call this like around the world or something, but it's really just rewriting logarithms as exponentials and exponentials as logs. Since they show the same information, you can rewrite one in the other. So you can rewrite as exponential as a log or a log as an exponential. Then the common logarithm, I'll just warn you right now, we use log base 10 a whole lot in mathematics and science. And since we use log base 10 so much, mathematicians as a whole decided, okay, I'm kind of sick of writing so many little 10 subscripts, so if I just write log x, just assume that I mean log base 10. So if you ever see log and it doesn't have a base, that means that it has a base of 10. And similarly, log base ex is used all the time. So since log base ex is used so much, mathematicians again got kind of lazy and they're like, 4 letters, that's too much to write. So here, let's write it as lnx for natural log, or log natural. So if you don't see a base on the log, then it's log 10, and if you see ln, that just means log base e. Okay. And this definition is kind of just restating what I stated there above for you. But let me show you some examples, because this will make more sense as you see some examples with numbers. So let's say rewrite the log as an exponential. First, let's do log base 2 of 2 is equal to 1. So if I'm going to rewrite this logarithm as an exponential, we'll start at the base. So log base 2, it means that I'm going to rewrite this as 2 to the power of 1 is equal to 2. Right, so it's as simple as that. We're just rewriting the log as an exponential. So let's try 2 more. Let's do log base 4 of 64 is equal to 3. All right, so log base 4 means that we're going to have a base of 4 to the 3rd power equals 64. And one more, let's do log 1/3, log base 1/3 of 81 is equal to -4. So that means 1/3 to the -4 power is equal to 81. And so that's how you rewrite logs as exponentials. And it turns out you can go in the other direction as well. We could rewrite exponentials as a logarithm. So we could start with something like 4 squared is equal to 16. And it turns out you do it the same way. We'll start with log base 4 of 16 is equal to 2. And I want to take a minute here to explain what does log base 4 of 16 mean and why is it equal to 2? Well, log base 4 of 16 is asking us the question, 4 to what power is equal to 16? Well, 4 to the 2nd power is equal to 16. That's why log base 4 of 16 is equal to 2. Because the log is saying the base to what power is equal to the argument. Let's take 2 to the 10th is 1024. If you wanted to rewrite this as a log, you would take log base 2 of 1024 is equal to 10. And again, what that log base 2 of 1024 means is 2 to what power is equal to 1024? It's 2 to the 10th power. That's why log base 2 of 10 to the 24 is equal to 10. Okay, we are going to come back to graphing these logarithms at a later date. So I would encourage you to pause the video and try these 4 on your own, and the answers there are included for you. But this is just like the examples we just did. As well with 5 through 8. 5 through 8 are just like the examples we've just done, rewriting exponentials as logarithms. And then for the next couple, I'm just erasing this so I can go through it with you guys in the video. The recording in class did not work right. That's why I'm going back and erasing here. But 5 through 8 are just like the previous examples as well, so you can pause it and try them and check your work against what's there. But let's start with 9 through 12. So in number 9, we have log base 4 of 64, and it doesn't tell us what it's equal to. That's what it wants us to find. It wants us to evaluate the logarithm, find out what that log is equal to. So log base 4 of 64 is asking us 4 to what power, so 4 to the question mark power, is equal to 64. So you can check by doing different powers of 4. You can do 4 to the 1st, 4 to the 2nd, or you could do 4 to the 3rd. And eventually you'll see one of these is 64. So that means that log base 4 of 64 is equal to 3. All right, log base 1/8 of 1 is equal to what? So this is saying 1/8 to what power is equal to 1? Well, anything to the 0 power is equal to 1. So this is just 0, because 1/8 to the 0 power is equal to 1. All right, I think 9 and 10 are problems that you may be able to do on your own without a calculator, without the help of a calculator. I think 11 is probably pushing it, because again we're asking 2 to what power is 1 over 32. That's probably hard for you guys to recognize that that's 2 to the negative 5th power. So what I would do is I would use a calculator to evaluate this, and Desmos has a calculator that works for it. If you have a TI, that also will work. Please come see me and I will show you how to use those to actually do these logarithms with a calculator. All right, and similarly with 12, 1/25 to the 1/2 power is equal to 1/5. All right, now earlier I had mentioned that logarithms and exponentiation are inverse functions. So if I have 13 to the power of log 13 of 6, that 13 having a power that's a logarithm of 13, those are inverse functions of each other. They undo each other. So what that means is that the 13 and the log 13 undo each other here, and we're just left with 6. And it works the other way as well. Here we have ln of e to the x cubed. ln and e, they're inverse functions of each other. Since they're inverse functions of each other, we're just going to be left with x cubed, because they undo each other. And then we can use this fact that these functions undo each other to actually find inverses of functions. So if we have y equals 15 to the x plus 10, and I wanted to find the inverse, the first step would be to switch x and y. And then we're trying to solve for y. So subtract 10 from both sides. And now we have y stuck in an exponent, right? It's stuck as an exponent for 15. Since it's stuck as an exponent for 15, we want to get it out of there using a logarithm, because the inverse of exponentiation is logarithms. So we'll take log base 15 on both sides. And you can see this log 15 and 15 will cancel each other out. And we'll just be left with y equals log base 15 of x minus 10. So that is the inverse function of y equals 15 to the x plus 10. And lastly, number 16 here, we have y equals ln of 2x minus 8. So switch x and y. And we're solving for y. So add 8 to both sides. And now you have you have got y stuck inside of a logarithm. So we're going to make both sides exponents for e. And I chose e because e and ln are inverse functions. So the e and the ln will undo each other. And we have e to the x plus 8 is equal to 2y. So y is equal to e to the x plus 8 divided by 2. All right, like I mentioned, we are going to come back to graphing in a little bit, but we'll end it here for today, and I'll talk to you guys soon.